here. We should see it here. Alright folks, so welcome to the next lecture in special relativity mathematical prerequisites. So today we're going to be building on one of the special topics we need to understand Maxwell's equations, and that topic is the idea of scalar line integrals. Now today we're going to take a look at line integrals for scalar fields, and tomorrow or in the next video we're going to look at it for vector fields. So go ahead, take a look at the thumbnail picture we have today and comment down below what do you think it means. In the meantime, we're going to go ahead and get started. Alright folks, if you're new to this series is basically devoted to the mathematical prerequisites you need to go ahead and hit the ground running in dealing with special relativity. Okay, now don't worry, while special relativity does require a lot of mathematical experience, we're going to go step by step in regards to every single topic you need to know for this amazing subject. Okay, now while we're loading that, I'd like to ask the audience a question, and I'm going to upload this question right here on the screen right now. Alright folks, welcome to the next lecture in special relativity mathematical prerequisites. Today we're going to be talking about line integrals, specifically line integrals over scalar fields. In the next video we're going to be talking about line integrals over vector fields, but today the main focus is over scalar fields. Scalar fields are basically functions that, given two or more inputs, provide only one output, as any scalar would do. Now this topic is essential not only for understanding special relativity, but Maxwell's equations. And as a matter of fact, we're going to find a way to connect Maxwell's equations with the Lorentz transformations, which are going to be the basis for special relativity. So before we go ahead and get started, I'd like the audience to go ahead and comment down below what you think the thumbnail for today's video represents. Good luck, and we will begin shortly. A lot of mathematical experience. So I'm kindly asking the audience for some patience while we go ahead and set up. But in the intervening time, I'd like to go ahead and get started with the actual slides that I prepared for today's lecture. Now today, no, we're not doing the 1, 2, 3s. We're doing line integrals, scalar line integrals, as a matter of fact. Okay. Now, just to give you a short 20-second review, scalar functions are those that have multiple inputs but only one output. Right? So multiple inputs all get mapped into one output. Okay. So let's go ahead and get started with line integrals. What is our first slide today? Well, first and foremost, we're going to be taking a look at the definition of line integrals, okay? Now, I'm actually going to need the charger for this one, my friend. We will give you this other Mac very soon. But let's take a look at the definition of line integrals right now. So, line integrals are really all about curtains, right? I'm sure you've seen a curtain before. I'm sure your window. Yes, 1 second, no. I'm sure that you have windows in your home. Oh no, we're gonna need this. I'll give you this one very soon. This one has 25. For example, let me show you what I mean. Let's say you have a window, right? I'm sure you have a window in your home, and every window has a curtain. So a curtain looks something like this, right? So every window has a curtain, and let's say you want to find the area of that curtain. What would you need? Well, surprisingly, you would need multivariable calculus, specifically line integrals. Now, let me elaborate on what I mean by that, okay? Let's say you go to the xy plane, okay? Let's say we're in R3. So we're in R3 and we go to the XYZ plane. So here I have the XYZ plane. Why don't you use the phone, my friend, mi amigo? Now, while my amigo is using the phone, let me show you what I mean by the line integral. Let's say I have some kind of a two-dimensional region in the XY plane. So, for example, it might look like some kind of a strange pancakey shape, right? And that shape, that weird distorted figure, is going to be mapped on to some kind of surface in 3D space, right? So for example, any point over here, let's say this point here, this point might be, I don't know, it might be, I don't know, give it a name. Maybe it's x comma, whoops, did I mess up everything? Clearly this session is not going well. Let's start over, shall we? Let's start over. So what I essentially have here is something like this. Let's check first and foremost that we are streaming. And here I have the XYZ, plain and simple. And here is my region of interest. And that region, some function f of x comma y is going to map that region onto a 3D surface, right? So every point here is going to be associated with a 3D surface. And that kind of bridge between 3D, between that golden 3D surface you see up here, that's highlighted in yellow, that bridge between this golden surface and this bottom 2D surface, that bridge is the area we want to calculate, right? The area of that bridge. Okay, so it's kind of like a mixture between a surface area and a volume, if you will. So we basically want to find the area of this region. Hopefully you understand clearly what I'm talking about. If not, let's head back to the thumbnail picture. Okay, here you see that we have, what do we have here? Let's go step by step. Here we have some kind of a region in two-dimensional space. It doesn't have to be a region, actually. It has to be a path, a line, if you will. So let me demonstrate that line to you right here in red. So let's pick up the red marker here. And if you can see what I'm highlighting right now, that's the path in the XY plane, right? And there's going to be a function. There's going to be a function f of x comma y that's going to map every single point on that curve, on that path in the xy plane to an actual height on the z-axis. So let me show you what I mean. So for example, path in the xy. So for example, this point right here over here might be mapped to this point on the z-axis, on the z plane, right? So hopefully you see what I mean by that. And the line integral, the scalar line integral, is going to calculate the area of this intermediary, of this bridge between the two-dimensional xy plane and the actual height of the surface. Okay, so now that you have some kind of an intuition of what I mean by a line integral. So what I'm going to do right now is go ahead to the next slide. And on the next slide, we're going to cover why we need the line integral, right? Why would anyone even care about the line integral? Okay. Now, before we do that, let me just comment down below for the audience, if there's anyone even watching, that right. Okay. So let's keep going. So what is the physics motivation for the line integral? Well, it's going to begin quite simply. Let's say you have a wire, right? Physics, we always want something tangible, and a wire is exactly that. It's pretty tangible if you ask me. So let's go ahead and do that. Unfortunately, it seems I've been murdered in some crisis, so let's save that and we should be good to go for that. So let's say I have some kind of a wire, right? Maybe I should draw it a bit thicker. So here's my wire drawn in black. Hopefully you see that wire, right? It looks like a path because that's exactly what a wire looks like, or at least what it's supposed to look like. Now this path is going to be defined. It's going to be defined as a function of f of x comma y, right? So for example, if I pick a random small, infinitesimally small slice of my wire, what's that going to look like? Let's zoom in on that small slice, right? So let's highlight that slice for a moment, and we're going to zoom in on that small red slice that you probably see on your screen right there. Okay, so let's look at that red slice. What is it telling us? Well, first and foremost, what do we want to find? What is the goal of using the line integral? Well, our goal is to find the total charge of this wire. So let me actually write that down. Our goal, do that. Well, the line integral gives us a way. Okay, so for instance, let's say the length of this infinitesimally small segment is a length ds, right? ds. Okay, just because in arc length we always use s for the arc length, so that's why I'll call that ds. Just for an infinitesimally small change in the wire length. Okay, so the length of that is ds. So far so good. But how do we get from ds to the actual total charge on that infinitesimally small piece? Well, that's why we have a function f of x comma y. That function is going to tell us what the charge density is on that specific portion of the wire. So we actually use the lowercase sigma to denote charge density, and to find that charge density we can simply plug in the position of our infinitesimally small point into our function. So for example, this point over here might be x of s comma y of s, right? So to find the charge density at that point, all I have to do is compute the value of my function, the value of my charge density at that point. So for example, instead of f of x comma y, I just plug in f of x comma s comma y of s, and that would give me the charge density at that specific portion of the wire. So now that I have the charge density and the length of the wire, all I have to do to find the total charge on that infinitesimally small piece of the wire is multiply them. So let me actually undo that. So if I have f of x of s comma y of s on this piece of wire, then what am I going to have for my total charge? Well, as I said, we're just going to multiply these two. And if I multiply these two, I'm going to end up with something like f of x of s comma y of s all times ds. But remember, we don't want the total charge over a small piece of the wire. We want it over the whole wire, right? So what do? We're going to take the sum of all of those small charge densities, right? The charge density here, charge density here, charge density here, total charge there. Okay, so we're going to add up all those total charges over those infinitesimally small paths of the wire, and what are we going to get? Well, let's duplicate this slide and move on to the next one to see what I'm going to get. So if I move on to the next slide, what I'm going to show you is how we can find the total charge across the wire. So let me erase all the things I have thus far, and let's find the total charge. So the total charge, as I mentioned, we had for one infinitesimally small region, path, keep that in mind, never region for this line integral. We're going to take the value of the charge density at that specific point, evaluate it, and multiply it by the length of that piece, of that path. But what am I going to do? I'm going to use sigma. So sigma I equals 1 to n pieces, right? And just put that in, right? So s sub I, so the ith piece, evaluate the charge density at the ith piece by putting in the point into the function f, multiplied by change of s, right? And what do I mean by change of s? Well, just to be absolutely concrete by what I mean, let me draw back my wire here. This for example, let me show you what I mean. So this over here might be the point x of si, comma y of si. Hopefully you see what I'm writing over there. And this point over here a bit later might be x of si plus 1, and this might be y of s sub I plus 1. Okay, so that's what I mean by the change in s. It's just going to be the difference of these two. Okay, okay, so that's good, but we're going to take the limit of this summation, right? Because taking the limit is going to make our approximation exact. So how do we take the limit? Well, that should be obvious. It's just going to take the limit as what approaches 0, the length or the number of pieces. The number of pieces approaches 0. So the limit as n approaches infinity. And by now you should be able to recognize what that is. The limit of a summation is none other than what? Audience, do we know? Do we know? Yes, audience has just told me that the limit of a summation is the integral. So I can actually just go ahead and write that down. The integral of f of x sub si, but not s sub I, because we're doing it over all the pieces. So just f of x of s, comma y of s, and instead of delta s, I can just put ds for a tiny differential in the change of the length. Okay. And what is our boundary? What is our domain? So our domain is simply going to be where the path starts from. So for example, s equals 0 to s equals l. L simply being the length of my wire. Okay, so that's going to give me a definite integral from s equals 0 to s equals l. And that, my friends, is the line integral. But I still can't compute that, right? So I have to change it into something that I can compute, right? So let's move on to the next slide so we can actually understand how we can compute this truly massive thing, integral. So what did I just get? I got the definite integral from s equals 0 to s equals l. L being the length of my wire, of f of x of s, hopefully you see what I'm writing there, comma y of s, all times ds, which is a tiny differential in my position. So ds. But I'm not done, because I actually can't compute it at all. Because remember that my wire was given as a function of not s, but t. Remember that, let me actually write it down. My function was given as a parameter of t. So okay, so what I know is my function as a parameter of t. I don't know how to evaluate my function as a parameter of s, but I do know how to evaluate it as a function of t. So what can I do? I can set s as to a function of t. So I can let s be a function of t by setting s equal to s of t. Now, instead of ds, what can I replace ds by? To replace ds by something, I need to know what ds is. So I'm just going to take the differential of both sides. So I'm going to have ds is equal to, well, it's simply the chain rule, right? The derivative of the outside, so s prime of t, times the derivative of the inside, dt. And because what am I differentiating in respect to? T, the common parameter, right? Okay, so now that I've done that, all I have to do really is replace that. But I still don't know what s prime of t is. I want to get that s prime of t as a function of just t or r. Okay, so how can I do that? Well, we have to hark back to the days of arc length. Okay, so let's go back to what an old topic, which is arc length. How do we find the arc length of a function? So let's go back to our basics. So here we are in the xy plane, and here's some crazy looking function f of x, right? So let's say my desired quantity is the arc length of f of x over this boundary, right? How do I find the length of that arc? Well, let's zoom in. And let's see how to compute that arc length. First and foremost, what I'm going to do is let's say this was an infinitesimally small slice, right? So then it would not look like a curve anymore, not like an arc anymore, but rather a line. And every line can be broken down into its components, right? This line, which we can denote as ds, can be broken down into its components. Its components can be as follows: dx, a small differential in x, and dy. So now we can actually express ds as a matter of fact, as such. We can write ds, let's zoom in. ds is equal to actually the square root of the sum of the squares of the tiny differential in x and tiny differential in y. Remember that dx and dy here are actually not derivatives. They're not functions at all. They're just infinitesimally small scalar quantities, which is a very important thing to emphasize. So now that I have that, I still don't know my function, my arc length as a parameter of t. So what do? Well, recall that I parameterized my function as a parameter of t. So x is equal to x of t, and y is equal to y of t. So as a matter of fact, I can write dx. I can write dx as x prime of t dt, and I can write dy as y prime of t dt. Okay, hopefully that makes sense. Now that I've done that, what are we going to go ahead and do? Let's go ahead and go back to our original slide on the notation. Okay, now that we have that kind of a sensibility on arc length, I'm going to take it a step further and show you how we can find the arc length for a parameterized function. Crazy word, but parameterized function. How can we do it? Well, let me first erase everything I have here. Okay, so here I have my xy plane, and here I have some wacky function. Now this function is going to be expressed as a parameter of t. So for example, this will be this position vector to this point. Let me actually use the thicker pen. So this position vector to this point is simply going to be r of t. Likewise, the position vector to this point is going to be r of t naught. Now the difference between those two is going to give us some approximation of the arc length. So the difference between these two, which is going to be delta r of t, is going to be simply what? It's going to be, of course, r of t minus, well, you know what, instead of saying of course, let me write that out. It's going to be r of t minus r of t naught. Right, so that's going to be a secant line. But as r of t approaches r of t naught, so as r of t approaches r of t naught, that delta r of t actually approaches r prime of t. So if we want to find the arc length over that infinitesimally small chunk, over that infinitesimally small piece, all we have to do is take the magnitude of the derivative of our function as a parameter of t. And that's going to be our infinitesimally small arc length, right? Hopefully that makes sense. Hopefully that makes sense, right? And this is ds, and we just learned that ds is equal to the magnitude of the derivative of our position vector as a parameter of time. Okay, now we understood how we can fully express our integral as a function of the parameter t. So now what can I do? Let's go back to slide number 5. Now I can, instead of writing s prime of t, I can just write what? I can just replace s prime of t by the magnitude of my function, my position vector, as a parameter of t. And boom, now my whole line integral is expressed as a function of my parameter t. So I can finally write the answer in red, the final thing in red. So the integral from t equals a to t equals b of what? Of f of x of t, comma y of t, times ds. So we're almost done here. So I'm going to multiply this by the magnitude of the derivative of my position vector in respect to time, and that's it. That right there, folks, is the line integral for scalar functions. That right there is the line integral and its definition. But we're not done. We are not done. We've covered the arc length. We've covered all of that. Now I want to hit on a geometric motivation for what we just learned, which is the line integral. So let's take a look at the geometric motivation behind all of this, okay? What do I mean by geometric motivation? Well, let's go ahead and go back to our XYZ coordinate plane. So if we go back to XYZ, and let's say we have our path, there's some kind of a wacky horseshoe magnet kind of path, and that path is going to be mapped to some values using f of x comma y function. So let's say you have something like that. Whoops. Okay, third attempt and final attempt. There we go. So each and every point on this path is going to be mapped to some z coordinate. So for example, let's say I take this point right here on my path, right? It's going to be mapped to, for instance, that coordinate. And this point is going to be mapped to another z coordinate, right? Likewise, every point is going to be mapped to some coordinate. We are almost done, folks. And we are basically finished with the problem. So, and by now you should already know that the line integral is going to give me the area, if you will, of this kind of three-dimensional region right there. But where does that come from? Well, let me give you the geometric motivation, right? So let's say we have a point over here. Let's say we have a point in the 2D plane, right? And we want to find the area of this infinitesimally small rectangle that's above that point. So this point might be on a rectangle that has a length of ds. Hopefully you all agree with that. ds, right? I'll write it in red so that it's visible. ds. Now, that point is going to be associated with some z value, right? Some value that the function assigns it. Right, so that point is going to be at f of x of s comma y of s, right? So that means the actual area of this infinitesimally small rectangle is going to be the length times the height, the base times the width. So what is my base? My base is ds. So actually let me draw that out. So the area of my infinitesimally small rectangle is going to equal two things: the product of the base, which is ds, times the height. And what is my height? My height is simply f of x of s comma y of s. So you can just write the ds afterwards, but essentially that's the geometrical motivation behind the scalar line integral. And second to lastly, I want to discuss. I want to make a remark on length. If my function that maps the every point on my path to some arbitrary z value, if my function that does that is actually equal to 1, so if f of x of y is equal to 1, then what will my line integral represent? In other words, if f of x of comma y is equal to 1, what is this going to equal? What is this going to equal? ds. I'm going to be left with simply the integral of ds. The integral of ds. And the integral of a derivative is just the derivative. So that's equal to s. And what is s? That's simply the actual length of my path. So if the function that maps your path to some arbitrary z value is simply 1, that means That means the line integral is simply going to be the length, the arc length of your path. Okay, and finally, after that remark on length, I just want to touch on a very quick example of the line integral, and that example is quite simple. I have it loaded up right here. So this is slide number 6, I do believe, so 6. So let's go ahead and do a very quick example. So here it goes. Let's say I have a function as follows. R of t is equal to cosine t, comma sine t, comma t. Now let me just go ahead and show you how we're going to visualize that. So that function is actually going to look something like a helix, like the DNA curve. So let me add what is it, space curve, and let's delete that, and instead of 0.1 t, it's just going to be t, and you can see how my curve actually looks in three-dimensional space, right? It looks something like the DNA helix. So let's zoom out and animate that, and you can see that's my curve right there, and it also shows you the velocity and acceleration vectors. Okay, now that you have a visualization of what we're dealing with, let me give you the domain over which we're dealing with it. So my parameter t is going to be defined over 0 to 2 pi. And lastly, my function that maps my points to an arbitrary z value is going to be in 3D, and it's going to be equal to x squared plus y squared plus z squared. Okay, so I have to compute the line integral for this. So we just have 2 more seconds to go. So this is going to be f ds. So what are we going to do? We're going to have, what are we going to have? Well, let's first find ds, right? ds is the easier one, I guess. So ds is equal to that, right? The magnitude of the position vector in respect to time. So let's find the magnitude of the position vector. So first and foremost, the derivative of the position vector is equal to minus sine of t, comma cosine of t, comma 1. That's going to be my derivative, and the magnitude of that we're going to compute on the next slide. So let's go ahead and calculate the magnitude of that on the next slide. So let me erase everything we don't need, right? So then I'm going to have the magnitude of the magnitude of r prime of t is simply equal to the square root of negative sine t squared. Oh, we're gonna need this. Oh, take this.
Excuse me, Professor.
Yes.
I think 40%.
Oh, no. Not.
This percentage lasts 2 minutes with the yellow brightness.
Please, you're interfering with the connection.
Please.
You broke the connection already, my friend. So, negative sine t squared plus cosine t squared. So hopefully you're still hearing my audio. Unfortunately, it was broken. Back to the question. So plus 1, and that's just a basic trigonometric derivative. So sine squared t plus cosine squared t is just gonna give me the square root of 2. Okay, but now I still need to find f as a parameter of t, and we're gonna finish that in the next slide. So thank you for watching, and we'll see you next time.